Now the last lab is pretty simple, lab 7, the hardware component. So the only difference between lab 6 and lab 7 is that we're going to sweep the input frequency here and construct the Bode plots, which is the magnitude and phase of the input to output response of the signal as a function of frequency. So for lab 6 we just use 1 kilohertz here. For this one we're going to use a range of 1 hertz or 10 hertz up to 10 megahertz if things work correctly. And you should see once you get to higher frequencies that the gain will start to decrease, the output amplitude will decrease, and the input and output will be offset from each other in time. There'll be some delay for the input signal to reach the output, and it'll be more apparent in terms of phase at those higher frequencies. So hardware is the same as it was for lab 6, literally no difference. Just make sure you're probing the output. Probably easiest if you probe after the capacitor so that it's centered at 0 volts. Doesn't have to be though, it might just make things easier for you. But other than that, I haven't touched the hardware from the previous lab. So inside of waveforms, I should probably mention, for checkoff for this one you want a picture of the hardware again, which will look the same as lab 6 probably, and a picture of the scope at 10 megahertz, or at 1 megahertz, sorry. And we're gonna fill out a bunch of data here, and that'll be it, and make some measurements based on the data. Okay, so right now I have the input signal set to I have 10 millivolts amplitude, so 10 millivolts peak to peak, and the frequency is 10 hertz, because that's our first data point. And what you want to get from this plot is the offset in terms of time and the differential gain. So the differential gain should be about constant for the lower frequencies, and you'll see it start to degrade once we get to higher frequencies. But as for what we put in this table here, input signal is going to be the same every time, so I use 10 millivolts, and I'm just going to populate that down. Okay, I don't know why it wanted to do that, but it's 10 millivolts all the way down the column. Output signal, you're going to do a better job at measuring it than me. I'm going to say it's 1.5 volts, and it automatically calculates the magnitude in decibels over here. And the time delay between signals, I'm going to tell you right now that it's pretty much 0. Actually, one thing to note, I have my inputs swapped. So let me swap them the other way around so that it'll make more sense, because right now there's a 180-degree shift. So in my circuit, I want to swap the input signals. So I'm going to move these 2 wires and swap it with the input on the other side. I was supposed to do this for lab 6 too, but it's not a big deal there. This is just changing the gain from being positive to negative, so that we have 2 inverting stages. Okay, so now if we go back to my waveforms, now they're in sync, and you can tell that there's almost no phase difference between the 2. And I'm going to make this a little easier for myself by adding an offset of maybe a millivolt, a couple millivolts, just so that they're like right on top of each other, so I can start to see when they go out of phase. Alright, so right now time delay is basically 0. And you're going to increase this frequency for the points that it says. I'm going to jump up to 1 megahertz. And we have to really zoom in on it now. You have to adjust the time scale every time you do this. I went the wrong way. Let's try 1 megahertz. So things look really jittery now, and you can see there's some time offset between the signals. So let's stop this real quick, and you can at least make out some kind of sine wave for the input signal. The output looks much cleaner, so that's nice. But you can assume the input's still 10 millivolts peak to peak. Output signal, you want to measure that and see how much it's changed. Looks like it's I don't know, maybe 500 millivolts peak to peak now. So this is 0.5. Time delay. You can export the data and figure out, you know, when what the delay is in the zero crossings, or you can kind of ballpark it if we have a number. I'm guessing we can use these in some way. Oh, neat. That tells you the difference between 2 points. Okay, so if we just kind of look at the peaks, so we want to do input to output, so yellow to blue. The delta time is telling us the delta y value. That's not useful. Delta x is 292 nanoseconds. So however you want to type this in into here, 292 nanoseconds. And from that it will automatically compute the phase in degrees. So it looks like it's a little past 90 degrees out of phase now. Let's try bumping this up to 10 megahertz and see how it behaves. This might not look pretty, but we'll try. And we have to zoom in on it again, so now we're at, yeah. Can't even really see the blue anymore. Maybe if we increase the resolution here. Yeah, it's just crazy. So you might not be able to make a measurement with this one. It's all over the place. So you can kind of see an input on the yellow, looks about right maybe. A bit noisy. I got a little exclamation point here. Device bandwidth limitation. So you might not be able to do the 10 megahertz measurement, but you should be able to get up to at least 1 megahertz. So you can get your picture up here along with at least your data up to this point. And from that you can figure out the AV, which for me was 43 dB, that's the gain at low frequencies. FP1 and F unity. You might not be able to get these numbers because we can't get the 10 megahertz or anything above that to work. So just kind of guesstimate these numbers and I'll be okay with it. Same thing with phase at unity and phase margin. Might not be able to get those with the hardware limitations that we have, but just kind of ballpark those. Okay, and you can use these plots that get generated to help with that. This first one will be the magnitude, and then this one will be the phase. And that's it for this one. There's one more lab, Lab 8, but it doesn't have a hardware component, so you're safe to dismantle everything on your board once you're done with this lab. Lab 8 is just simulations.